Welcome to class.
Number bases simply express a system of counting in mathematics. There are different systems of counting in mathematics, from base 1 to several other bases. The base 1 is called unary. Base 2 is binary. Base 3 is ternary or trinary. Base 4, quaternary. Base 5, quinary. Base 6, centenary. Base 7, septenary. Base 8, octave. Base 9, nonary. Base 10, decimal or denary. The base 10 is the everyday number we use. For example, if I say I am 12 years old, that 12 expresses 12 base 10. Usually for all number bases other than base 10, their base is written beside them. If I write a number like this in base 2, this is not called 10, it is called 10, and I will have to write it beside it. If I write a number like this in base 3, this is not called 102 because this is not base 10. This is base 3. So I have to write the base. The moment you don't write the base of a number beside it, it definitely means that that number is a number in base 10. For every other number other than a number in base 10, you have to write the base beside it. There are higher bases than base 10. We have base 11, base 12, base 13, and so on. Another very important thing you have to know in number bases is that in any base, there is never a digit, a single digit that is up to the base or more than the base. For example, the only digit in base 1 is 0, because I said in every number base there is never a single digit that is up to the base or more than the base. So this 0 is the only digit in base 1. Base 2 numbers are called binaries, and there are only 2 digits in base 2, which are 0 and 1. In base 3 is called ternary or trinary, and the only digits in base 3 are 0, 1, and 2. These are the only digits in base 3. I believe by now you are already helping me mention the digits in base 4 as 0, 1, 2, and 3, because there is never a single digit that is up to the base or more than the base. So let's keep counting down and look at base 10. Base 10, that is denary. The digits under base 10 are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the digits in base 10. What we call 10 in base 10 are 2 different digits, which is 1 and 0. When we go to higher bases, base 11, base 12, and higher bases higher than base 10, base 11. Under base 11, we have digits from 0, 1, and so on up to 9, and what is supposed to come up as 10 under base 11, because we know that for base 11, 10 is less than 11. So there is what we call 10, but it is not written as 10. It is written as A, because it has to stand as a single digit. For base 12, we have 0, 1, 2, and so on, up to 9. Then what is supposed to come up as 10 is written as A. What is supposed to come up as 11 under base 12 is written as B. I hope we understand this. Let us learn to place value on the digits of different number bases. I am going to be starting from base 10 because that is what we know. Let us start from what we know to what we don't know. I'll be making use of this example, which is 98,405. 98,405. We want to place value on these numbers. The place value of this 5 is 10 raised to power 0. The place value of this 0 is 10 raised to power 1. The place value of this 4 is 10 raised to power 2. The place value of 8 is 10 raised to power 3. The place value of 9 is 10 raised to power 4. All these place values are in terms of 10. You can see there are different powers of 10 because this is a number in base 10. Using the knowledge of indices, we know that anything raised to power 0 is equals to 1. And that is why this 10 raised to power 0 is equals to 1. 10 raised to power 1 is equals to 10. 10 raised to power 2 is 10 times 10, which is equals to 100. 10 raised to power 3 is equals to 1,000. 10 raised to power 4 is equals to 10,000. And that is where the different place value gets their name from. The 1 is called ones or units. The 10 is called tens. The 100 is called hundreds. The 1,000 is called thousand. The 10,000 is called tens of thousand. I believe we remember this. And that is how each of the digits gets their place value. Now, let us go to other bases we are yet to learn about. For example, numbers in base 2. 1,0,0,1,0,1 is a number in base 2. And because it's a number in base 2, all its place value is going to be in terms of 2, just like we place value on 10. The place value of this last one, yes, is very important for us to write the base. If the place value of the last one is 2 raised to power 0, the place value of this 0 is 2 raised to power 1. This is 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, and 2 raised to power 6. 2 raised to power 0 is equals to 1, and that is units or ones. 2 raised to power 1 is equals to 2. 2 raised to power 2 is equals to 4. 2 raised to power 3 is 8. 2 raised to power 4 is 16. 2 raised to power 5 is 32. And 2 raised to power 6 is 64. So, if we are going to be placing values on this number in base 2, 11,0,0,1,0,1 in base 2, the place values are 1s, 2s, 4s, 8s, 16s, 32s, and 64s, and so on. We can have higher ones. Does that sound interesting? Let us look at base 3. To place value on it, because it's a number in base 3, the place value of the last digit will be 3 raised to power 0. The place value of this one will be 3 raised to power 1. The place value of this is 3 raised to power 2. The place value of this is 3 raised to power 3. The place value of this is 3 raised to power 4. The place value of this is 3 raised to power 5. Converting them, 3 raised to power 0 is equals to 1. 3 raised to power 1 is equals to 3. 3 raised to power 2 is 9. 3 raised to power 3 is 27. 3 raised to power 4 is 81. While 3 raised to power 5 is going to be 243. So if you have to talk about the place value of 120112, which is a number in base 3, the place values are 1s, 3s, 9s, 27s, 81s, and 243s. So this number means we have 243, 281, 027, 1913, and 2 ones or 2 units. You will appreciate it better by the time we get to conversion of other bases to base 10. For other bases like base 4, the place values will be powers of 4. Other number bases are also like that. Just like we have whole numbers in base 10, we also have fractions in base 10. The fractions in base 10 are called decimals. The whole numbers in base 10 are called denaries. In fact, we can use the 10 interchangeably. That is the same way we have fractions in other bases as well. 987.65. This is a number in base 10. Once you see me write any number without writing the base, that means it's a number in base 10. We want to place value on these numbers that involves whole numbers and decimals. Just like we started from the last among the whole numbers, I am starting from there again. A number in base 10. So the place value of this 7 is 10 raised to power 0. The place value of the 8 is 10 raised to power 1. The place value of 9 is 10 raised to power 2. Now I go to the decimals. The place value of the 6 is 10 raised to power minus 1. The place value of this 5 is 10 raised to power minus 2. We know that 10 raised to power 0 is 1. 10 raised to power 1 is 10, which is 10. 10 raised to power 2 is 100. For 10 raised to power minus 1, 10 raised to power minus 1 means 1 over 10. 10 raised to power minus 2 means 1 over 100. This is units. This is tens. This is hundreds. 1 over 10 or 10 raised to power minus 1 is tenths. And 1 over 100, which is the same thing as 10 raised to power minus 2, is hundredths. Do you remember this pattern of placing value from lower classes? That is how they find their names. If we have to expand this number using their place value, let us do that. This is 900, 900, 900. This is 8 tenths, 8 tenths, which means 8 times 10, which is 80. This is 7 ones or 7 units. 7 units is 7 times 1, which is 7. This is 6 tenths. 6 tenths means 6 divided by 10. 6 divided by 10 is 0.6. All these also have decimal points behind the units. So let's fix the decimal points. And we are going to fill the other spaces with zeros before we add up. This is 500. 500 means 5 divided by 100. 5 divided by 100 is 0.05. So this is 0.05. Let's fill the empty spaces up with zeros. Then we add up. So here I have 0. Let's add them up. We have been able to expand using the place value. So the value of 9 is 900. The value of 8 is 80. The value of 7 is 7. The value of 6 is 0.6. And the value of 5 is 0.05. When we add up, we are going back to where we started from, which is 987.65. It is with this same knowledge of place value in different number bases, we will be converting numbers in other bases to base 10. Let's go. 101.11 in base 2. Let's place value on it. We start with the unit. The decimal point is always at the back of the unit. So let's start. Because this is a number in base 2, this is going to be 2 raised to power 0. This is 2 raised to power 1. This is 2 raised to power 2. Going to the bicimals. This is 2 raised to power minus 1. And this is 2 raised to power minus 2. Very similar to when we have numbers in base 10. 2 raised to power 0 is equals to 2. 2 raised to power 0 is equals to 1. 2 raised to power 1 is equals to 2. 2 raised to power 2 is equals to 4. 2 raised to power minus 1 means 1 over 2. 2 raised to power minus 2 means 1 over 4. That is 1 over 2 raised to power 2, which is 1 over 4. So, looking at the value of each of these numbers, it means we have 1 fourth, 0 twos, 1 ones, 1 halves, 1 quarters. Let us expand the number the same way we did with numbers in base 10. This is 1 fourth, which means 1 times 4, which is 4. This is 0 twos. This means 0 times 2, which is 0. This is 1 ones. 1 ones or 1 units. 1 ones means 1 times 1, which is 1. This is 1 halves. 1 halves is just 1 times half, which is half. Half is 1 over 2. Half is also 0.5. So I go with the decimal, which is 0.5. Of course, the decimal point will also be at the back of this. We are taking them now to base 10. This is 1 quarters. 1 quarters. 1 quarters, which means 1 times 1 over 4. 1 times 1 over 4 equals to 1 over 4. 1 over 4 is the same thing as 0.25. So I have 0.25. I want to add it up to get the value of this number, 101.11 base 2. I want to get the value now in base 10, the equivalence of these digits, this number in base 10. So I'll be filling all empty spaces above with zeros. So let's add up. This means I have 5, 7 points and 5. This means that 101.11 in base 2 is equivalent to 5.75 in base 10. This is just the basics of conversion of other bases to base 10. Thank you for watching. Please subscribe to our channel for more interesting lessons.